Hermeus has officially taken flight with their quarter-horse Mark 1 technology demonstrator, marking a huge step toward their goal of fielding fully reusable hypersonic aircraft for the US Air Force.
The US just flew a hypersonic jet, and they said Mach 5 was impossible. For 50 years, every aerospace textbook on Earth drew the same hard line. Past it, metal melts, engines eat themselves, air turns into a wall, and anything man-made that tries to push through it comes apart in seconds. That line just got crossed.
The pace of innovation has basically declined to near zero within aviation, and the ability to rapidly iterate to design requirements that are bespoke is something that doesn't really exist anywhere. It can happen in small pockets, but we are turning cycles that people haven't turned in decades.
Above the Mojave Desert, a vehicle the size of a fighter jet tore through the threshold. Every physicist on the planet swore couldn't be survived and walked away from it. What happened up there isn't a leak. It isn't a rumor. It's already on record. And once you see how they pulled it off, you will never look at the sky the same way again. The race to Mach 5. For decades, the SR-71 Blackbird wore the crown as the fastest air-breathing jet ever built. A long, black titanium ghost that screamed across the stratosphere at over 2,190 miles per hour, more than 3 times the speed of sound. Nothing touched it.
The Blackbird was revolutionary because it was the first aircraft designed for sustained flight at 2,000 miles per hour. It was the first stealth airplane ever designed.
The Blackbird retired in the late 1990s, and the world quietly accepted that extreme speed in the atmosphere had hit its absolute ceiling. Then a small company in Atlanta decided to ignore that ceiling entirely. Hermeus was founded in the late 2000s by A.J. Piplica and a group of engineers who had already worked on real high-speed flight for the US Air Force, SpaceX, and Blue Origin. They had built things that actually flew. They came together around one shared conviction. The wall everyone kept slamming into wasn't a physical law. It was an engineering problem. And engineering problems have solutions. Their target was simple to describe and almost impossible to deliver. A reusable aircraft cruising at Mach 5, roughly 3,800 miles per hour, sustained long enough to carry passengers or fly repeated military missions. Not a one-shot weapon, not a prototype that burns up on its first run. A real aircraft that takes off, completes the mission, and lands. Mach 1 is the speed of sound, about 760 miles per hour. Most long-haul jets cruise at roughly Mach 0.85, around 575 miles per hour. New York to London at that pace takes 7 to 8 hours. Engineers reserve the word hypersonic for anything above Mach 5, where you're covering close to a mile every single second. Hold that speed across the Atlantic and the crossing drops to roughly 90 minutes. Your coffee from the New York airport is still warm when you land in London. That is the vision.
What if breakfast in New York and lunch in London were possible on the same morning? Not someday, right now. A secret aircraft just shattered every speed record ever set. The technology inside breaks the rules of physics. Scientists said it was impossible. The Pentagon proved them wrong.
Here is what nobody in the industry wants to say out loud. Every serious attempt to get there before Hermeus either melted, failed, or got quietly canceled. While commercial aviation slowed down after the Concorde era, the world's military powers sprinted the opposite direction. Russia began publicly demonstrating the avant-garde hypersonic glide vehicle, a warhead that rides the edge of the atmosphere at many times the speed of sound while actively maneuvering toward its target. China unveiled the DF-17, a ballistic missile that releases a hypersonic glider capable of skipping along the upper atmosphere and changing direction mid-flight. Both are described openly as operational systems. The problem is brutally simple. American missile defense was engineered around objects that follow predictable, arching paths. A hypersonic glider at Mach 10 doesn't follow those paths. It flies lower, it moves faster, it changes course, and it arrives before any defending system has time to respond. But the deeper strategic issue isn't the incoming threat, it's the gap on the other side. A missile is a one-shot tool. What the US military has publicly described as the real prize is something different, something reusable, something that flies the mission and comes back, and nobody on Earth has ever built one that works. That gap is what Hermeus is trying to close. The reason nobody has closed it yet is that the moment you try, physics stops being a textbook and starts trying to kill you. If a story like this, an engineering problem disguised for 50 years as a physical law, is the kind of thing you want more of, hit subscribe right now. We dig into the machines and the people quietly rewriting what the world thinks is possible. And we are just getting started. Why physics doesn't want you to do this. Speed isn't the hard part. Heat is. When a spacecraft like Crew Dragon returns from orbit, it hits the atmosphere at extreme velocity, glows white hot, and endures enormous thermal stress, but only for a few minutes.
And there we have confirmation of splashdown. Dragon has returned to planet Earth. It is now back home, and you can see on your screen our two fast boats racing out to the capsule, now in recovery.
The entire design goal is to slow down as fast as possible. A hypersonic aircraft is the exact opposite problem. It doesn't want to slow down. It has to accelerate to Mach 5 and hold it, not for minutes, for hours, cruising, sustaining, carrying fuel, sensors, electronics, and eventually human passengers through conditions that should rip a normal aircraft apart. At those speeds, the air slamming into the leading edges doesn't behave like a fluid anymore. The compression is so violent that the air itself heats up before it ever contacts the metal. A phenomenon called aerodynamic heating. Temperatures on sharp leading edges at Mach 5 can exceed 1,000 degrees Fahrenheit. Aluminum melts. Titanium loses structural strength. Seals burn. Fuel lines overheat. Standard electronics simply die. Hypersonic flight isn't a speed problem, it's a heat problem. And it has stopped nearly everyone who has tried to solve it. Two of the most famous aircraft ever built show how far the world got before that wall ended the attempt. Concorde proved that civil aviation could sustain Mach 2, cutting the New York to London crossing to about 3.5 hours. The airframe heated so much in flight that the entire metal structure grew several inches in length. Engineers had to build deliberate expansion gaps into the design just to keep it from tearing itself apart. After a catastrophic crash near Paris in 2000, it was retired in 2003. Mach 2, less than halfway to where Hermes is going. The SR-71 Blackbird proved something different. Built largely from titanium, it flew so fast and so hot that the fuel tanks couldn't even be sealed on the ground. The jet literally leaked fuel onto the runway before every mission, and only stopped leaking once the metal expanded in flight and closed the gaps. Even the Blackbird never reached Mach 5 in sustained level flight. Mach 5 in a reusable aircraft is the next stair on that staircase. And it still should not be possible, which is exactly why the engine Hermes built is so hard to explain without sounding like you're making it up. The engine that shouldn't exist. Most people stop at the airframe when they look at a hypersonic aircraft. They see the sleek pointed shape and assume the fuselage is where the hard problem lives. It isn't. The real story is the engine. Hermes calls it Chimera. A conventional jet engine is brilliant from takeoff through modest supersonic speeds. Spinning turbine blades pull in air, compress it, mix it with fuel, ignite it, and push exhaust out the back. But as the aircraft goes faster and the incoming air gets hotter, those same spinning blades become a liability. At high Mach numbers, performance falls off a cliff. A ramjet solves the high-speed problem by eliminating mechanical complexity entirely. It's a shaped tube with no spinning parts. The vehicle's own velocity rams air into the intake with such force that the geometry compresses it through aerodynamic shaping alone. Fuel injects, combustion happens, exhaust rushes out. But there's a catch. A ramjet produces essentially zero thrust when the vehicle is slow. You can't take off in one. It only works once you're already going fast enough. Chimera does both.
We just demonstrated mode transition, which means we went from running in turbojet mode to ramjet mode. This is probably the most critical challenge in unlocking hypersonic flight.
At low speeds, it operates as a conventional turbine-based jet engine. As the aircraft accelerates, it transitions. Airflow is redirected around the turbine core into a separate ramjet duct, where combustion continues without rotating components. One engine, two completely different operating modes. What sounds clean in a summary is, in physical reality, something closer to a controlled explosion happening inside a machine that cannot afford to fail. Because the hard part isn't either mode, It's the moment between them. Hermes calls it the Valley of Death. Picture this. Inside the University of Notre Dame's Turbomachinery Laboratory in 2022, it's late at night. The team has been at this for hours. Air is feeding into the intake at simulated high-speed conditions, the equivalent of Mach 4 from the engine's point of view. The turbine section is doing its job. Instruments are reading nominal. Then someone in the control room calls the transition. For a fraction of a second, neither the turbine nor the ramjet has full authority. The turbine is winding down. The ramjet duct is opening. The airflow is being redirected in real time at conditions no conventional engine test has ever recreated on the ground. The engineers are staring at three numbers at once. Airflow can't stall. Combustion can't drop below the threshold needed to sustain thrust. And pressure can't spike in a way that would, in flight, tear the engine apart. Get it wrong, and the aircraft falls out of the sky. They make it through the valley. The mode switch holds. They run it again. It holds again. Over roughly 5 months of these late-night runs, they push Chimera through much of its planned speed range. From the moment they walk into that lab to the moment they have a confirmed, repeatable mode transition. Less than 2 years pass. On a budget of tens of millions of dollars. By defense acquisition standards, that is almost offensively efficient. But the engine they used at Notre Dame was only the warm-up. The one that has to actually fly is a much harder beast. The heart of the machine. The first version of Chimera used the General Electric J85 turbine core. Compact, reliable, good enough to learn on. But Piplica and his team always knew the J85 was a placeholder. To chase Mach 5 class speeds, they needed something far more serious. So they reached for the Pratt & Whitney F100. Same engine family that has powered F-15 Eagles and F-16 Fighting Falcons for roughly 50 years.
It seems Hermes are well on their way with the development of their ramjet engines, with both the J85 and much larger F100 versions being actively worked on.
In modern variants, the F100 puts out around 29,000 pounds of thrust in afterburner and has accumulated over 28 million flight hours. One of the most battle-tested high-performance turbine cores ever built. And here's the catch. Even that engine can't survive what Mach 5 does to incoming air on its own. At those speeds, air arriving at the engine intake is hundreds of degrees Fahrenheit before any compression has happened. Feed it straight into the F100's compressor and the internals warp, crack, and self-destruct in seconds. The engine eats itself. The fix is a pre-cooler, an extraordinarily dense heat exchanger sitting behind the intake with thousands of tiny channels packed in tight. Incoming air rushes through it and dumps thermal energy in the fraction of a second it takes to transit through. Hermes plans to manufacture the pre-cooler from nickel-based alloys using advanced 3D printing. It's the only way to produce that geometry at all. Paired with the cooled air, the F100 can operate at higher speeds and efficiency than it was originally designed for, smoothing the transition into ramjet mode and narrowing the Valley of Death. This is where the Jacksonville Heat Facility comes in. Hermes runs combined pre-cooler and F100 tests at a ground site in Florida built inside former Navy test cells from the 1950s and 1980s. HEAT stands for High Enthalpy Air Breathing Test. Walk through the place and you can feel the lineage. Concrete bunkers, scarred steel, instrumentation panels glowing in the dark. A.J. Piplica describes the philosophy in 4 sentences. Build it, test it, break it, fix it. In an industry where engine programs routinely span decades, that's almost radical. The hardware keeps working. What it hasn't done yet is fly, and that is the only test that ultimately counts. Quarter horse from the ground up. You don't build a Mach 5 aircraft by starting with a Mach 5 aircraft. You build stairs. Hermes organized those stairs under the name Quarter Horse, a structured progression of test aircraft, each designed to prove something specific and hand the knowledge to the next vehicle. In 2021, the U.S. Air Force and venture investors together awarded around $60 million to fund the series. The approach mirrors what made companies like SpaceX disruptive. Design hardware, build it, test it hard. Roll the lessons forward. The first vehicle, Mark 0, never left the ground. A full-scale structural mock-up an iron bird used to validate hydraulics, fuel lines, wiring, landing gear, and the remote flight control architecture Hermeus calls the flight deck.
They just tested Quarter-Horse Mark 0, the ground vehicle we saw being constructed in the factory. This vehicle was intended to help Hermeus develop their in-house manufacturing techniques. A lot has changed since the days of the SR-71, and this has unlocked many manufacturing techniques that the engineers of the 1960s could only have dreamed of.
Its job was to surface integration problems before anything important was on the line. Then came Mark 1, the first quarter-horse aircraft built to fly. An unmanned demonstrator powered by the General Electric J-85, with a short, highly swept wing optimized for high-speed performance. Hermeus and the Air Force took it to Edwards Air Force Base in California, where virtually every major American record-setting aircraft has been tested. Late May 2025, the remote pilot team, operating from a ground control station at Edwards, brought the aircraft to rotation speed. It lifted off. It flew its planned test pattern. Control surfaces responded exactly as the computational models had predicted. The math was right. Mark 1's mission was deliberately narrow, proved that an airframe shaped for high Mach performance could still take off and land from a conventional runway on ordinary landing gear. Non-negotiable if future hypersonic aircraft are ever going to operate from standard bases. Box checked, next stair. Quarter-horse Mark 2.1, roughly the size of an F-16, unmanned, powered by the F-100 core that will eventually integrate with Chimera's full combined cycle system.
So our first variant of quarter horse, Mark II will be around pushing the jet engine up in flight to the mode transition point. So making sure the right flow is being fed to the engine, making sure our pre-cooler works in the actual environment.
In early March 2026, Mark 2.1 took off from Spaceport America in New Mexico for its first flight, using restricted airspace over White Sands Missile Range. Hermeus describes it as the opening act of a Mark II series that will progressively push through transonic, supersonic, and eventually high Mach territory. It's designed to exceed Mach 2 as testing progresses. Mark 2.2 and Mark 2.3 follow. All of it is the warm-up. The real target is quarter-horse Mark 3, the first vehicle planned to carry the complete Chimera, two-engine, and attempt the live mode transition from turbine to ramjet in actual flight. Take off under turbine power, accelerate through supersonic, close the turbine flow path, open the ramjet duct, keep accelerating. If Mark 3 does that cleanly in the sky, it'll be something never achieved in a reusable aircraft in human history. A door no one has opened, but the hardware is just the beginning of what changes if it works. What Mach 5 actually unlocks. The speed only matters if it does something real in the world. Two applications define what Hermeus is building toward, and they sit at opposite ends of the spectrum. The first is Dark Horse, a reusable hypersonic drone designed exclusively for defense missions. Roughly 45 feet long, targeting around Mach 5, using the same hybrid engine architecture as Quarter Horse. Unlike a missile, it flies the mission, returns to base, and goes again the next day.
Assuming each mark of the Quarter Horse is a success, Hermeus will be moving on to build their second vehicle, Dark Horse, which will be a fully reusable uncrewed vehicle designed for defense and national security missions. It will be Hermeus's primary defense product, likely serving a similar role that the SR-71 did before it.
Picture what that changes operationally. Instead of a conventional reconnaissance aircraft, spending hours approaching a defended coastline, trackable, predictable, vulnerable, Dark Horse departs from an ordinary runway and sprints to its objective at several thousand miles per hour. It can cross a body of water the size of the South China Sea in well under an hour, execute its mission, and exit the threat envelope before air defenses mount an effective intercept. The speed itself becomes a form of protection. But speed alone isn't the trick. The real power is what you can pack into a single fast pass. A Dark Horse sortie could simultaneously map radar installations, identify which systems activate in response, and relay that intelligence to assets still hundreds of miles out. On the next run, the same aircraft might carry electronic warfare gear to suppress those systems during a follow-on strike. The second application changes the civilian world entirely. Hermeus calls it Halcyon, A roughly 20-seat, the hypersonic passenger jet, targeting Mach 5 with approximately 4,600 miles of range, focused on more than 125 long overwater routes. New York to Paris in around 90 minutes. Ticket pricing aimed at the premium business class market. Halcyon would cruise at altitudes approaching 90,000 feet, nearly 3 times higher than a conventional airliner, where the sky goes dark blue-black overhead, and the curvature of the Earth becomes visible from the window seat. You can't accelerate a cabin full of people the way you push a drone. Pressurization, climb profile, emergency systems, and survivability all have to be solved for an environment where conventional escape mechanisms are useless. One regulatory obstacle sits entirely outside Hermeus's control. Since 1973, the United States has prohibited routine supersonic commercial flight over land because of sonic booms. Any hypersonic airliner would face the same restriction. NASA and Lockheed Martin's X-59, with its dramatically elongated nose designed to reduce the boom to something closer to a soft thump, made its first flight in late 2025 and is now entering community overflight tests.
At NASA, we're working to usher in a new era of supersonic flight. Meet the X-59, our quiet supersonic airplane that will turn loud sonic booms into quiet sonic thumps. From nose to tail, the X-59 is designed for quiet supersonic flight. The X-59 is almost 100 feet long, with a nose that's longer than the average school bus.
If regulators are persuaded, overland restrictions could eventually be relaxed. Halcyon would benefit directly. Hermeus isn't alone in the broader race. Stratolaunch has already flown its Talon A reusable hypersonic test vehicle beyond Mach 5. In Pentagon-backed trials in late 2024 and March 2025, the Talon A2 was dropped from a carrier aircraft, lit its rocket engine, exceeded Mach 5 over the Pacific, and landed at Vandenberg Space Force Base, the first reusable American hypersonic test asset since the X-15. On the civil side, Boom Supersonic's XB-1 prototype has already broken the sound barrier, building toward the Mach 1.7 Overture airliner. And Europe's reaction engines spent more than 30 years developing its Sabre combined jet rocket engine with a sophisticated pre-cooler before running out of funding and entering bankruptcy in late 2024. The engine never flew. What Hermeus has that reaction engines didn't at the critical moment is working hardware that has left the ground, a funded Air Force partnership, a methodology that generates real flight data. Quarter Horse is flying. Chimera has demonstrated mode transition on the ground. Mark 2.1 is already in the air. And here is where the title finally pays off. The aircraft that breaks the SR-71's record won't just be faster. It'll take off from an ordinary runway, not a launch pad, not a carrier aircraft. A regular strip of concrete you could land a business jet on. It'll cross an ocean in the time it takes to watch 2 movie trailers, execute its mission, and land. And then, the part that quietly rewrites everything. It'll refuel, sit on the ground for a few hours, and do the exact same flight again the next day. No throwaway stages, no expensive rebuild. Just a plane and a runway and a speed the textbooks still insist isn't supposed to be achievable. If this story makes you feel like it still shouldn't be possible, good. That feeling is the point. Every stair Hermeus climbs is one that 50 years of aerospace history said didn't exist. Drop a comment below and tell me, would you actually board a hypersonic jet at Mach 5? Or does 90 minutes between New York and Paris sound a little too fast for comfort? I want to hear it. Now check out the videos on screen for more stories that shouldn't be possible, but turned out to be completely undeniably true. We'll see you there.